What is mathematics about? Why is there a controversy about the foundations of mathematics? The accepted foundation of contemporary mathematics is built upon the Zermelo-Fraenkel set theory and the axiom of choice, which expanded upon Cantor's set theory. Proofs, disproofs, and the formal mathematical system are based on first-order predicate logic, which was created independently by Gottlob Frege and Charles Sanders Peirce. These two had actually created their own versions of first-order predicate logic without the knowledge of the other creating it, but later they were combined into the system of logic we have today. It is also worth noting that not all of mathematics can be explained with first-order predicate logic. Some of mathematics requires a higher-order logic to explain. Gottlob Frege, known as the founder of modern logic and the father of analytical philosophy, was a mathematics professor at the German University of Jena. Charles Sanders Peirce was an American philosopher and mathematician who is sometimes known as the father of pragmatism. He was a lecturer at Johns Hopkins University and also gave lectures at Harvard and the Lowell Institute, which is now known as the University of Massachusetts at Lowell, or UMass Lowell. Funnily enough, my father actually graduated from this university. Gödel was known as one of the principal founders of modern mathematical era in mathematical logic. He is known for his incompleteness theorems, which talk specifically about arithmetic but can be expanded to include the rest of mathematics. He is also known for his completeness theorem, which pertains to first-order predicate logic itself. The completeness theorem is worth researching on your own if you want. While many argue that mathematics can be reduced to logic, it has been proven that it cannot be entirely reduced. Gödel was the first to prove this with his incompleteness theorems. Despite the name, the theorems do not directly concern completeness, rather they concern the notion of decidability. Definition: a formal system is decidable if and only if, for any sentence P of that formal system, either P or its negation is provable. This is also known as the law of the excluded middle, or indirectly known as the principle of bivalence. The law of the excluded middle and bivalence are not exactly the same, as bivalence says a declarative proposition is either true or false, while the law of the excluded middle says a declarative proposition or its negation must be true, but not both, though they are entirely related. The first incompleteness theorem states that if arithmetic is sound, it is undecidable. That is, there is a system or a sentence in arithmetic that neither it nor its negation is provable in arithmetic. The second incompleteness theorem states that if arithmetic is sound, then it cannot prove its own consistency. That is, it cannot be proven that arithmetic never permits the proof of a contradiction. Here we will consider the outline of the proof for Theorem 1. Let G be a declarative proposition stating this sentence is not provable in arithmetic. After stating this proposition, Gödel does some honestly amazing things translating G into Gödel numbers, which is a way of representing a formal logic sentence in arithmetic. I won't pretend to understand how Gödel numbering works, so you can research that on your own if you want. I have linked in the next slide, I believe, or 2 slides after this, a video on Gödel numbering. All right, step 1 of the proof. Assume arithmetic is sound. Next, assume we can prove G. If we can prove G, then inherently G is false, because G states that it is not provable in arithmetic. Hence, we cannot prove G. Therefore, G is true. In conclusion, if arithmetic is sound, then this sentence is not provable in arithmetic. Here we will consider the outline for a much shorter proof for Theorem 2. First, state G. This sentence is not provable in arithmetic. Step 1. Assume arithmetic can prove itself consistent. So, G is proven, but G states that G is not provable. Contradiction. Therefore, arithmetic cannot prove itself consistent. As I could spend hours discussing Gödel's incompleteness theorems and Gödel numbering, here is a more in-depth video over the topic created by Numberphile. Even though I wish to be an expert in mathematics, logic, and inherently mathematical logic, I am not yet one, so I cannot begin to fathom the incompleteness theorem proofs in their entirety. Instead, here is a link to Stanford's website where they detail the proof of the first incompleteness theorem. You will need to scroll down a bit to find the proof, but these links are listed in my references slide. Now it's time for the controversy. Naturally, Gödel's theorem sparked an outroar from mathematicians around the globe. Some believed Gödel had undermined the very fundamentals of mathematics. However, this major controversy does not lie with Gödel, it actually lies with the ZFC set theory. One axiom in particular, the axiom of choice. There was also much controversy about another concept of Cantor's, so it became known as the continuum hypothesis. It was the first on Hilbert's famous 1900 list of 23 problems to prove or disprove. By the time Gödel came around, he had introduced a model of the other ZF axioms in which both the axiom of choice and the continuum hypothesis were true. But in 1963, other models were created in which either AC or CH, or both, were false. Thus, AC and CH are independent of each other and of the other ZF axioms. So, guess what? Just like how we have Euclidean and non-Euclidean geometries, we have equally valid Cantorian and non-Cantorian set theories. Now let's think about something. If mathematical creations are merely arbitrary fancies, how is it that some of these creations turn out to have physical applications? For example, the applications that enable us to calculate the orbits well enough to put people on the moon. When the Greeks developed the theory of ellipses, they had no inkling that it would have applications to a space race. Well, this just shows how mathematics is ever-changing, alive, and incomplete. There is always something new to discover in mathematics. There are likely countless branches of mathematics that have yet to be discovered. And lastly, here I have listed the references I used to create this presentation. The last two are textbooks, but the first four you can use to learn on your own.